So, yeah, let's do that. I mean, like, let's see what is the limit of physics of how big can a casting machine be? Let's find out.
Around 1,000 welding robots are about to be phased out at the Texas factory. A production line capable of building a vehicle in under 30 seconds is being set up, and a machine with up to 50,000 tons of clamping force is preparing to shake the entire automotive industry. It sounds unbelievable, but this is how Elon Musk plans to bring Tesla back to its golden age with technologies designed to push the limits of physics. To make this happen, Tesla's CEO has introduced the fourth generation of the Giga Press, specifically engineered to manufacture the company's most advanced vehicles. With up to 50,000 tons of clamping force and a footprint roughly the size of a house, the machine could produce an entire vehicle structure at an almost unimaginable speed. So what exactly is Elon Musk's plan? And how could this machine disrupt the entire automotive industry? Here's what's really happening. The story really begins with a question Elon Musk once asked.
I mean, like, let's see what is the limit of physics of how big can a casting machine be?
This wasn't just a catchy slogan. Tesla has spent years turning that question into a real engineering challenge. The first Giga Press machines gave Tesla the ability to replace dozens of individual parts welded together with much larger single-piece aluminum castings. But if 6,000 tons were enough to transform the way the Model Y was manufactured, and 9,000 tons pushed those boundaries even further, then jumping all the way to 50,000 tons would mean something entirely different. This is no longer simply about building a bigger machine. It's an attempt to find out whether the entire logic of vehicle body manufacturing can be pushed to an entirely new level. So why does Tesla need a Giga Press with 50,000 tons of clamping force?
So I mean, we got to jam the liquid metal in, cool it down real fast, and then I guess maybe we need to just get even bigger casting machines. Sure, why not? Let's 50,000 tons.
To understand why 50,000 tons matters, we first need to understand exactly what that number represents. The Giga Press doesn't use 50,000 tons of force simply to press aluminum into a mold the way we might imagine a gigantic press machine working. That figure primarily refers to clamping force, the force used to hold the two enormous halves of the mold tightly locked together while molten aluminum is injected inside. When molten metal is injected into the mold cavity at extremely high pressure, it creates a force that tries to push the two halves of the mold apart. The larger the mold, and the greater the pressure and surface area involved, the more tremendous the required clamping force becomes. If the clamping force isn't sufficient, the mold can actually separate at the most critical moment of the cycle, ruining the entire casting and potentially allowing molten metal to escape. And this is where the 50,000-ton equation becomes truly intimidating, because Tesla isn't just trying to create a larger component, it wants to create it much faster. According to Elon Musk, the goal of the new system is to push manufacturing speeds closer to those of an electronics production line, with each cycle reportedly taking around 5 seconds and the ability to process multiple components within a single cycle. But achieving that kind of speed means Tesla can't simply increase the clamping force and hope everything works automatically. The entire process has to be synchronized down to the second. It all starts with the aluminum. Fresh material, along with recycled aluminum from previous casting cycles, can be fed into a furnace and heated to around 850 degrees Celsius or 1,562 degrees Fahrenheit until it becomes molten metal. Once surface impurities are removed, the molten aluminum is transferred into an enclosed holding furnace where the temperature is carefully maintained within the proper range so the metal is always ready for the next injection cycle. Available technical documentation describes a two-furnace system. One furnace is responsible for melting the aluminum, while the second keeps the molten metal at a stable temperature before it is injected into the mold. But even here, Tesla still has to solve a problem that's invisible to the naked eye. Molten aluminum reacts with its surroundings and can contain trapped gases or unwanted particles. That's why the system uses a controlled gas environment, argon degassing, and silicon carbide filters to remove larger impurities. Only after the metal reaches the required level of purity is it ready to enter the most critical stage of the entire process, the casting mold. Before each cycle, the mold is coated with an extremely thin layer of lubricant to ensure that the finished part can be removed easily afterward. The system then creates a vacuum inside the mold to remove trapped air. This is a crucial step because when you're trying to produce a massive structural component at extremely high speed, even a small amount of trapped gas can become a serious problem for the quality of the final product. Once everything is ready, a high-speed piston drives the molten aluminum into the mold cavity with enormous force. And from that moment on, everything happens in an incredibly short amount of time. The hardest part is being fast without sacrificing precision. If the metal is injected too quickly, trapped air or flow-related defects can compromise the internal structure. But if it's injected too slowly, the aluminum can begin to cool before the entire mold is filled. And when you're dealing with a massive component, a tiny section of the mold failing to fill properly can turn the entire part into scrap. Tesla has described the process as a delicate engineering challenge in which the metal must cool properly, while every post-casting step has to be automated to transform that scorching hot casting into a usable structural component. And this is why the cooling system is just as important as the clamping force. When the freshly cast component is removed from the mold, it can still be close to 400 degrees Celsius or 752 degrees Fahrenheit. It is then sent through a cooling system to rapidly bring its temperature down, while the mold itself must also be cooled, cleaned, and prepared for the next cycle. According to technical documentation, the entire sequence is synchronized so precisely that the next casting cycle can begin just 1 to 2 minutes after the previous one. Excess aluminum is trimmed away and fed back into the melting process, helping minimize material waste. Finally, the finished component is inspected using X-ray imaging to detect internal defects that would be completely invisible to the naked eye. Now, you might be wondering, why go through all this complexity just to make one massive component? Because every part you eliminate from a vehicle also eliminates an entire chain of work from the factory. That is the real power of the Giga Press. A traditional vehicle is made up of hundreds of individual components, which are then joined together using welding, bolts, rivets, adhesives, and various other connection methods. Every joint represents another manufacturing step. Every step requires equipment, and every piece of equipment requires factory space, maintenance, and quality control. Tesla is trying to reverse that entire logic by turning dozens of smaller components into a much larger integrated structure. According to available documentation, Tesla has been targeting roughly 80 major structural components for the Cybercab, compared with around 200 for the Model Y. If that figure holds up in actual mass production, it would represent a major shift in vehicle architecture. And think about it this way: if a single component can replace dozens of smaller parts, Tesla isn't just saving assembly time. It can also eliminate welds that could potentially become weak points, reduce the number of mechanical connections, and create a more continuous structural design. But there's an important misconception here. People often assume that if a structural assembly consists of 70 welded components, you can simply replace whichever individual piece gets damaged. But if those 70 components are consolidated into one massive aluminum casting, even a crack in one small area could mean replacing the entire casting. In theory, that sounds perfectly reasonable. But in reality, repairability depends on how the manufacturer designs the vehicle's crash absorption zones and the repair procedures that go along with them. It's not simply a matter of how many individual components make up the structure. Tesla now provides dedicated repair procedures for the Model Y's rear mega casting. In many areas, Tesla allows technicians to cold straighten bent sections, weld small cracks, reinforce damaged areas with reinforcement plates, and even replace individual sections of the rear rail instead of replacing the entire casting. Only when the damage affects critical areas or exceeds certain limits does the entire casting assembly need to be replaced. In 2025, Thatcham Research, a UK-based organization specializing in automotive repair and risk research, published the results of 2 years of crash testing, damage assessment, and repair work performed directly on the Tesla Model Y. They found that the mega casting was not only repairable, but in the cases they tested, it could actually be less expensive to repair than a traditional multi-piece steel structure. Compared with the conventional rear structure used in the Model 3, repairing a damaged section of the Model Y was approximately $2,800 cheaper, while replacing the entire casting was still around $675 cheaper. So the problem with Giga casting was never that one crack means you have to throw away the entire car. What really matters is how Tesla designed that casting to be repaired. And at least with the Model Y, real-world crash testing has shown the opposite of the initial concern. In some cases, repairing the mega casting can actually be cheaper than repairing a structure made up of dozens of individual components welded together. Tesla is trying to automate fewer steps while making each individual step capable of doing much more. Instead of having hundreds of robots working together to assemble countless small pieces, a single Giga Press can perform one operation that produces a massive structural component. That's the difference between simply automating an old factory and redesigning the factory so it no longer needs many of those old manufacturing steps in the first place. And if the 50,000-ton target can actually become a reality in mass production, the competition will no longer simply be about which automaker owns the most powerful casting machine. It will become a competition over which company can design a vehicle that is best suited to a massive casting machine. Because you can't take a vehicle designed around traditional manufacturing methods and simply put it into a Giga Press. To fully take advantage of a machine this massive, engineers have to rethink the shape of the structural components, how forces are distributed, how the part is cooled, how it is removed from the mold, where the connection points are located, and how the entire component will be integrated with the rest of the vehicle. In other words, the Giga Press doesn't just change the factory, it forces Tesla to change the way the vehicle itself is designed. And that may be why the Cybercab is expected to become the first product to use Tesla's latest generation Giga Press. Elon Musk has emphasized that the 50,000-ton Giga Press could potentially cast 5 vehicle bodies in a single cycle. This further supports the Tesla CEO's claim that the Cybercab could become the fastest mass-produced vehicle ever made, with production volumes potentially exceeding those of the Model 3 and Model Y combined. So how exactly does the Cybercab fit with the Giga Press? At first glance, the idea seems somewhat contradictory. The Cybercab is smaller than the Model Y, yet Tesla is considering a Giga Press that is vastly larger. If the vehicle is smaller, why would Tesla need a much bigger machine? Put simply, Tesla doesn't want to use the 50,000-ton Giga Press to make a larger vehicle. It wants to use it to cast more parts of the vehicle in a single cycle. With the roughly 6,000-ton Giga Press currently used for the Model Y, Tesla has already been able to turn the rear body into a single large structural casting, replacing dozens of smaller components and hundreds of welding operations. The company then applied a similar approach to the front body. However, these two sections are still produced in separate casting cycles, which means the vehicle body still has to go through additional processes to connect those large structural castings together. The 50,000-ton Giga Press, if it achieves the targets described in the proposed design, would take this concept to an entirely different level. Instead of casting the rear body and front body separately, Tesla wants to move toward producing the entire Cybercab body structure in a single casting cycle. This is exactly why the clamping force has to increase so dramatically, even though the Cybercab is smaller than the Model Y. As the scope of a single casting expands, the mold surface area increases, the amount of molten aluminum that needs to be injected increases, and the forces acting to separate the two halves of the mold increase as well. So the 50,000 tons of clamping force isn't about making a bigger vehicle. It's about combining more manufacturing steps into a single cycle. If this becomes a reality, Tesla could continue eliminating robots, joints, and assembly operations while dramatically reducing production time. And that is the real meaning behind the question Elon Musk once asked: how big can a casting machine be? Elon Musk isn't just trying to find out how big a machine can get. He wants to find out how much of a vehicle a single casting can produce. Tesla is exploring an even more radical idea for the Cybercab, integrating color directly into the material of the body panels instead of producing bare metal panels and then sending them through a multi-layer paint system. If this technology can work at scale, Tesla wouldn't simply have a faster Giga Press. It could also begin eliminating one of the largest and most energy-intensive areas of a factory, the paint shop. We'll take a closer look at this in the upcoming episodes, and that brings us to the end of today's episode. What do you think about the way Tesla is reinventing the vehicle manufacturing process? Drop a comment below. See you next time.